Swayam Prabha, Digital India, Educated India.
Hello everyone, welcome to the first tutorial on classical mechanics, and today we will be looking at problems related to accelerated frames of references. So we'll go to the first problem in the tutorial. A pendulum is suspended vertically in a stationary train compartment. The train then starts accelerating at an acceleration A. Write down the force balance in the frame of reference of the moving train and in an inertial frame of reference. So for the first problem, we have a train that is moving on a platform, let's say, and it's moving with an acceleration A. So let's take the acceleration to be along the x direction. So x is horizontal direction, y is in the vertical direction. Let's say the train is accelerating with an acceleration A along the horizontal direction. Now a pendulum is suspended from the vertical, and we'll have to calculate this angle theta later on. So pendulum is suspended, and the question is to write the force balance in the frame of reference of the moving train and in an inertial frame of reference. So the frame of reference for the moving train, let us consider that there's somebody standing inside the train observing the pendulum. And this person is also traveling inside the train, so the person is also accelerating with an acceleration A towards the right. And there's another person who is an inertial observer who's standing on a platform far away, observing that the pendulum is accelerating and also the train is accelerating with an acceleration A. So now we'll have to write down the force balance from the non-inertial observer. This person is the non-inertial observer, a non-inertial frame, and this person who's stationary is the inertial observer. So we'll have to write down the force balance in these two frames of reference. So let us start with the inertial observer. So what he sees is that there's a pendulum suspended on a train, and the pendulum is accelerating with an acceleration A towards the right. So he would say that there's the tension force which is acting on the pendulum. The mass, let's say the mass is m, there's a tension force which is acting on the mass, and there's gravity that is acting on the mass. And these are only two forces that he will consider in this problem. So this is for the inertial frame. Okay, so the inertial frame, in the inertial frame, the inertial observer would just say there are two forces that are acting on the mass m, and he will write down the force balance, saying that there are only these two forces, and total force acting on this nothing but T plus mg should be equal to the F net, which is the total force acting on it, acting on the total force acting on the mass m. So this is nothing but the mass times the acceleration of the body or the pendulum, the mass m. So it's mass times acceleration. The inertial observer knows that the train is accelerating at an acceleration a. So you would say that T plus mg is equal to m times a. So this is the force balance for the inertial observer. So next is the non-inertial, in the non-inertial frame. What happens? So in a non-inertial frame, you have a pendulum, the pendulum being suspended. There's another observer who's observing the forces that are acting on it. So the observer would say there's tension force, there's a gravity force, the weight of the mass that is acting on it. But since the non-inertial observer knows that he or she is in a non-inertial frame, he or she would put a fictitious force, F fictitious, in the direction opposite to the direction in which the mass is accelerating in the inertial frame. So for the non-inertial frame, we'll have to add a fictitious force, F fictitious, which will take into account the fact that the frame of reference is accelerating. So in this frame of reference, we will write down the force balance moment. So for this person who's observing this pendulum, he or she would say that the pendulum is stationary with respect to the observer. So the pendulum is not moving or accelerating with respect to the observer. So the force balance would read m plus mg, t plus mg plus f fictitious should be equal to F net, the total force acting on it, which is mass times the acceleration. But in this frame of reference, the pendulum is not accelerating, so this is equal to 0. Okay, so this is the force balance in the non-inertial frame of reference. And one might ask, what is this F fictitious? So F fictitious is nothing but for a linearly accelerated frame is nothing but minus of m times a plus a is to the right. So in terms of vectors, this would be minus m a e x hat. So it's to the left. So this is the fictitious force that the non-inertial observer would have to add to take into account the fact that the frame of reference is accelerating. Now let's go to the next part. What is the position of the, so this is the A part, we have wrote down the force balance. Next part is what is the position of the pendulum as found in both the frames of references. So there's just one generalized coordinate which we need to worry about, which is theta. Once we know theta, we can find the coordinate x and y. Since the length of the pendulum, the length of the string which is from which it is suspended is fixed. So once we know theta, we know everything. So we'll just have to find what is theta. So I'll go to the next page. So B, what is the angle the pendulum makes with the vertical? So again, let's start with the inertial frame. We have written down the force balance. It's nothing but T plus mg is equal to mass times acceleration. So mass times acceleration, acceleration is to the right. So we have taken the x-axis to be along the direction. So it's ma times ex hat. And now your T, the tension force, is nothing but it has two components, one along the x direction and one along the y direction. So T vector is nothing but T cos theta along the y direction plus T sin theta along the x direction. And the weight, gravity is acting on the minus y direction, so we'll have to write this as minus mg ey hat should be equal to ma ex hat. So this is nothing but T cos theta minus mg times ey hat plus T sin theta times ex hat should be equal to m times a ex hat. So from this we can equate these two terms. We can take each component and put it to be 0. So we get T cos theta equal to mg and we get T sin theta equal to mass times acceleration. So by dividing these two equations, what we get is that tan theta is equal to A over G. So which means theta equal to tan inverse of A over G. So by knowing the acceleration of the train, one can find theta, or vice versa. One by knowing the angle theta, one can also determine the acceleration of the train. So this is the inertial frame. Let's go to the non-inertial frame just to see what the non-inertial observer finds. So in the non-inertial frame, you have T plus mg plus f fictitious equal to 0. So T again we write it as T cos theta Ey hat plus T sin theta Ex hat minus mg Ey hat. So f fictitious, as I said before, should be opposite to the direction in which the time is accelerating. So it's in the minus direction. So it's minus m times a Ex hat equal to 0. Okay. So now we'll have to take each and every component and put it to be 0. So we get T cos theta equal to mg and T sin theta equal to ma. So again, we get theta equal to tan inverse of a over g. So as we can see, both the frames of references give the same angle, just that the force balance in these two frames of references are different. And the non-inertial observer would have to add a fictitious force in order to take into account that the mass is stationary, but the frame of reference is accelerating. Whereas the non-inertial observer will have to just write down the force balance as it is without adding any fictitious force, and you will have to say that the net force on the object is non-zero, and this is what gives the object acceleration. So that brings us to the end of the first problem. So now we'll go to the second problem. So the second problem is in a rotating frame. First problem was on a linearly accelerating frame. The second problem is in a rotating frame. So we have a system that is rotating about an axis, and since any point on this rotating, let's say, surface has a velocity that changes direction, at least with respect to time, which means that the frame of reference is accelerated. So we'll now look at a system which is rotating and try to understand how does the inertial frame and the non-inertial frame differ. So let's go into the problem. So problem number 2, a flour grinding machine or a mixer has a drum that is rotating with an angular velocity omega. The spinning drum has some quantity of flour in it, and we assume that the flour is almost a rigid object with a flat surface on the top. An ant suddenly falls onto the surface of the flour. After stabilizing itself, it tries to escape by A, walking straight towards the center in the frame of reference with a constant velocity. So the ant is, let's say, falls on top of some flour grinding machine or a mixer and then tries to walk towards the center. And then that is part A. Part B, it tries to walk away from the center in this frame of reference. And part C, it moves vertically downwards. So these are the frames of references with respect to the ant. So this is the rotating frame of reference. And the question now is to sketch qualitatively the path of the ant in an inertial frame of reference in each of the above cases. So let's start with the description. So we have the rotating drum with the flour, and we are supposed to take the top surface to be flat. So this is rotating, let's say, with rotation rate omega, which is given, and let's say on the top surface we have the point O, which passes through the axis of rotation, and there's this point A at which the ant is situated. And the A part is that the ant walks towards the center. So in that sense, it has a velocity v, let's say, which is going towards the center. So it tries to walk towards the center with the velocity v. and B, it's a constant velocity B. With the constant velocity V. This is from point A to point O. And in D, the ant tries to walk away from the center with a constant velocity V. And in part C, the ant is walking vertically downwards with a velocity V. So we'll try to sketch qualitatively the path in all these frames of references. So let's start with A. So we have, I'll just draw the top surface, and we have a point O, we have a point A, and the ant is moving towards the left with the velocity V. And what we will do is to also look at it from the top. So we have a point O, we have a point A, and we have velocity V. So in the rotating frame, the ant is just looking at the center and it's working towards the center. Whereas an inertial observer, let's say somebody who's standing outside the mix cell, say you or me, would just see that the ant is not only walking towards the center, but it's also rotating. So the ant, if let's say the distance between the center and the ant is r, we know that in solid body rotation, the ant will also have a tangential velocity of r omega. It's rotating about an axis. So the ant will not just have a velocity along the x direction, but in the let's define some axis. So let's say x and y, for example. So the ant will not just have a velocity along the direction joining O and A. It will also have a velocity in the perpendicular direction or a tangential direction. So we will define two sets of coordinates, x and y being the inertial set of coordinates and x prime, y prime being the non-inertial or rotating set of coordinates. So x and y are rotating, whereas x, y are fixed. So actually, the ant has a velocity along minus x prime, whereas it also has a rotating velocity along the y direction, y prime direction, which is not uh, present in the frame of reference, which is rotating actually, but it's seen from the frame of reference of the inertial observer. So this rotating velocity is what gives the x prime and y prime. The fact that x prime and y prime are rotating is what gives the rotation of the ant. So it compensates for the rotation of the ant. Whereas for an inertial observer, the fact that the ant is rotating is clearly seen because the ant will have a tangential velocity in the frame of reference of the inertial observer. So the inertial observer, I will draw the axis for the inertial observer, which is again x and y. At any given instant, the inertial observer would see that the ant has a velocity which is directly pointing towards the center, which is O, but it also has a velocity in the tangential direction. So effectively, the ant will move along the direction which is the sum of both. So it would be an inward spiral. So any later instant, again there will be one component along this direction, another component in the tangential direction. So it will move somewhere in between these two. So this effectively gives some kind of an inward spiral in the frame of reference, in the inertial frame of reference. Okay, this is what is observed in the inertial frame, whereas in the non-inertial frame or the frame of reference of the ant is just walking in a straight line towards the center. So it just continues to walk on a straight line. Whereas the inertial observer would have not just a velocity along the line connecting the ant and the center, but also a tangential velocity because it's rotating, and in the inertial frame, the ant will move on a spiral which is going towards the center, or an inward spiral. So this is the qualitative picture as asked in the question. We will come back to the quantitative analysis a bit later. So we can rederive these equations or these parts in a more quantitative way, which we'll come back in a bit. So now let's go to part B. So in part B, the ant is not moving towards the center, but it's moving away from the center. So again, if you look at the system from the top, we see that there's the center O, there's the position A, and the ant is moving away with the velocity v, and we have these two axes x and y, which are in the inertial frame. So at any given point, let's say x prime and y prime are the axes for the non-inertial frame. So at any given point, the ant is moving towards the center, but it also has a tangential velocity because it's rotating, which is seen from the inertial frame, whereas in a non-inertial frame, since the frame itself is rotating, the tangential velocity is not seen. So for the inertial observer, one gets that at any given time there's a velocity which is both radially outwards, going outwards, and in the y direction. So the ant would move somewhat in the direction that is it's sum of these two. So the ant would move along some direction which should go outward while also rotating. So this is nothing but an outward spiral. So again, here in this case, the ant in the non-inertial frame would just be moving in the x prime y prime axis. Let's say, since this axis is rotating, it no longer sees the fact that the ant is rotating, so the ant will just move away along a straight line. Similarly, for case A, the x prime y prime axis is the non-inertial axis. The ant would just move on a straight line towards the center from point A. Okay. Now let's go to part C, which is when the ant moves downwards with a constant velocity v. So I go here, so C part. But now the ant is moving in the vertical direction, so we'll have to see from both top and on the side. So in the top frame you have O, you have A, and the ant has a velocity which is going into this view. It's going downwards, and the question is, how does the ant move in the inertial frame of reference? So we will again construct x and y frames of references for the inertial frame. So the ant, instead of the ant just moves vertically downwards and with a constant velocity, but also rotates. And this rotation, while also moving downwards vertically, what that gives is that we have a rotation, and so we'll have to, it will be a sum of the rotation and the velocity downwards. So it will be a motion which will be rotating while also moving downwards. So this is nothing but a downward helix. So this is a motion which, let's say you have a screw and you're trying to put the screw inside a board. So any point on the screw would be going inside while also rotating. So it's a rotating, or it's a downward helix. which is the path which the ant takes in the inertial frame. The non-inertial frame, say x prime, y prime, since the frames are rotating, the ant would just be walking side downwards. So in terms of x, y, x prime, y prime, z prime, 3 dimensions, the ant is just moving vertically downwards. Whereas in the 3 dimensions, in the inertial frame, the ant is moving on a downward helix. So these were just qualitative pictures to get to understand how the ant is moving in the inertial frame. But we can do slightly better. We can also write down the quantitative trajectory. So we can exactly write how the ant moves as a function of time. So that we will call it a quantitative analysis. So here we will have x, y axis, which we have defined as the inertial frame axes, and we will also define x prime and y prime, which are rotating. So one quick observation that one can make is that any point along x prime axis, let's say it's where the ant is located, and this in the non-inertial frame, the ant is not moving away from x prime axis. So x prime axis, it's either moving close towards the center or going away from the center, or it's moving vertically downwards in the z prime axis. But along in the x prime direction, its position is always along the x prime direction. So what we can do is from the inertial frame, we can consider this position in terms of polar coordinates. So we'll take the direction x prime as the radial direction. So this will become our r in the inertial frame, and this will become our theta. The angle which x prime makes with x-axis as our theta, and since this is rotation omega, the position of the ant is basically given by 2 coordinates r and theta. So in the inertial frame, position of the ant is given by r and theta. Whereas in the non-inertial frame, its position is nothing but r times ex prime. That's it. Whereas in the inertial frame, let's say at t equal to 0, its position is given by r er hat. The er hat is the direction along the x prime direction as measured on the axis x and y. Now let's go to part A. In part A is to write down the velocity in the inertial frame. So what has been given is the velocity in the lap frame is what we need. So the velocity in the rotating frame or the non-inertial frame is given. So I'll just write this ROT is the rotating frame or the non-inertial frame or the frame of reference which is attached with the ant. So in the rotating frame, we know that the ant in part A is just moving with velocity v in the minus x prime direction. So we have minus v ex prime. So from the course we have studied that the velocity vector in the inertial frame can be related to the velocity vector in the rotating frame using this equation by adding omega cross r. So this is the relation that was shown in the class. So we just use this. So we have already found what is v. We already know what is v rotational. We just have to find omega cross r. Omega cross r is nothing but omega is along the z direction, positive z direction. We'll just write it as omega ez hat, cross. So R we are interested in R in the inertial frame. So we'll just say R as R ER hat. So EZ cross ER would just be E theta. So we'll write this as omega R EZ cross ER, which is nothing but omega R E theta hat. So this is the term here. So we finally get V inertial to be given by minus V Ex prime hat plus omega cross R vector. So minus V Ex prime hat, we can also write it as minus, since Ex hat is along ER hat, so we write it as minus V ER hat. Omega cross R becomes omega R E theta hat. Now, any position R and theta, and let's say we want to find the velocity of this point as a function of time, we just have to differentiate, and what one gets is differentiate this, and what one gets is R dot ER hat plus R theta dot E theta. So this is the velocity in polar coordinates. So we can relate this and this, and what we get is R dot equal to minus V and theta dot equal to omega. And so this is the expression for the velocity in the inertial frame. So once we have R dot equal to minus V, we can V is a constant, so we can get R equal to R naught minus Vt, whereas theta dot equal to omega gives theta equal to theta naught plus omega times t. So R naught and theta naught are just the initial position and the initial angle which x prime makes with the x-axis. So R and theta are known when you know the initial position V and omega. So now we can try to plot this. If one tries to plot this in the inertial frame, what one gets is an R which is decreasing with time, but a theta which is increasing. So one gets an inverse spiral. This is an equation for a spiral. So quantitatively, we have good agreement with our naive qualitative analysis. So this part is just to get back the same expression, or get back an expression which will say that our qualitative analysis was more or less correct, which gives more proof to our qualitative analysis. So the inertial observer just see the ant going on a spiral, and he can actually, if he knows the velocity in the non-inertial frame and the rotation rate, he or she can write down the solution as a function of time. So next, part B, we'll have to consider the ant moving away from the center, and we'll just do the same analysis as in part A. We again have two axes, x and y, and we have again x prime and y prime, and here the ant is moving towards the center, and we'll again write V inertial equal to V in the rotating frame plus omega cross R. So from the previous analysis, nothing much has changed except that V dot is given to be plus V Ex prime hat or ER hat. These both are the same. So V dot is plus V ER hat. So this is the only part which is different, whereas rest and all is same. So we'll just write V inertial to be equal to V dot plus V ER hat plus omega cross R. And omega cross R can again be written as omega EZ hat times R ER hat. And this is nothing but your E theta, so this gives V ER hat omega R E theta. So this is the same as this expression, just that you have a plus, instead of a minus here, we have a plus V. So we can again, we'll just integrate this again. So we'll write where V inertial is nothing but from the expression we got before. It's V ER hat plus omega R E theta hat. And in polar coordinates, we'll write this as R dot ER hat plus R theta dot E theta. And we get R dot equal to V and theta dot equal to omega. So now we get R equal to R naught plus Vt and theta equal to theta naught plus omega t. So we can try to again draw the expression for the path taken by the ant in the inertial frame. So R is linearly increasing with time, as theta is also linearly increasing, so it will be an outward spiral. So now we'll quickly go to part C. So now the ant is moving vertically downwards. So we'll write it as V lab or V inertial actually. Or inertial frame, some people also call it the lab frame. But V in the rotating frame plus omega cross R, and now V rotating is, it's in the minus, so it's going vertically downward, so it's minus V EZ hat plus R omega E theta hat. So again we'll write, so now instead of using just polar coordinates, we'll have to go to cylindrical coordinates here, R theta and Z. So we'll write it as Z dot EZ hat. So the expression in cylindrical coordinates is R dot ER hat plus R theta dot E theta hat plus Z dot EZ hat should be equal to minus V EZ hat plus R omega E theta hat. So this is the velocity in cylindrical coordinates. And this gives R dot equal to 0, theta dot equal to omega, and Z dot equal to minus V. So R equal to R naught, theta equal to theta naught plus omega t, and Z is nothing but Z naught minus Vt. And this is nothing but your downward spiral. So theta is increasing with time, whereas Z is decreasing with time. Now let's go to the next part. So now we have the next part, which is take the velocity to be v vector, mass to be m, and the frictional force acting in the plane perpendicular to the rotation axis to be f. So there's some kind of a frictional force that is acting on the ant, which is acting only on the plane perpendicular to the rotation axis. So it's only in the xy plane, and it's given by f vector. The only forces that act on the ant are the normal force, its weight, and the frictional force. So these are the only external forces that act on the ant. And one has to find the expression of f vector in all these three cases. So given the three external forces, how does one find the frictional force? And it's given that the frictional force is acting in the plane perpendicular to the rotation axis. Now, instead of writing just the velocity, one should go into the force balance, because we have to find the force. So again, we'll use the expression that has been taught in the class. So what we will do is, we will say that the total force that is acting in the inertial frame as F, we'll call this F lab. A total force acting in the rotating frame, we'll call it FR. It's the rotating frame. So I'll just make it smaller, F bar and F lab. So F lab is the inertial frame, total force acting in the inertial frame. F bar is total force acting in the non-inertial, not rotating. So these two can be related by this expression, which says that F, the rotating frame, is nothing but F in the lap frame minus, so now we'll have to add the fictitious forces, minus m d omega by dt cos r vector minus 2m omega cross v as measured in the rotating frame minus m omega cross r. So I'll explain what are these three terms. So this is the expression which was found in the class. So these three terms are fictitious forces. The first one comes from the fact that the rotation axis is not constant. Either the axis is changing or the rotation rate is changing. The second term is the Coriolis term, which comes from the fact that we are in a rotating frame, and the final term also comes from the rotating frame. This is the centrifugal term. So these are the fictitious forces that one has to add in order to compare the total forces acting in the lap frame and in the rotating frame. So we know that the ant in the rotating frame, so for a non-inertial observer, the ant is not accelerating, it's either moving in a constant line towards the center, away from the center, or moving vertically downwards. So this implies that the rotating frame, total force acting on it should be equal to 0. So this is in the rotating frame. So with this knowledge, we can just say that 0 equal to F lab minus, so d omega by dt is 0 because the rotation is constant, omega is constant. So this gives minus 2m omega cross v, rotating frame minus m omega cross r. So in F lab, we have the external forces. So these are the only two forces that act on the system. So this is nothing but n. These are three forces, n, m, and f, and the frictional force. So we'll write F lab as some n vector plus mg vector plus f frictional force. So I'll write it as f subscript FRIC, which denotes the frictional force. Now we know that the normal force is in the direction along the z direction, mg force in the minus z direction. So we'll write this as n minus mg times ez hat plus d frictional force. This is just to write down the expression for F, the total force acting in the lap frame. So, or the inertial. So now we'll have to find out these two terms also. So omega cross v, rotating frame. So for part A, so let's go to part A. This is nothing but omega Ez hat cross. So now we are writing down the expression for the velocity in the rotating frame, and we know the velocity in the rotating frame is along the minus ex prime hat. So it's coming along the x prime, it's moving in the x prime direction, but it's going towards the center. So it's minus ex prime. So again, z, I'll also put a prime just to say that we are now in the using the x, y, z prime directions. So this is nothing but omega Ez prime cross minus Ez prime times the velocity v. Then this is nothing but omega cross v. Omega is omega Ez prime hat. So this is in the z direction, and p is going inwards. So it's moving along this direction with the constant velocity v. So this gives Ez cross ex y, that there's a minus sign. So this is minus v omega ey prime hat. and we'll just also find omega cross r. So omega cross r is nothing but omega ez prime hat cross omega ez prime hat, and r is nothing but r times ex prime. So again, ez prime cross ex is along ey prime direction, and ez cross ey is along minus ex direction. So this let you verify is on minus omega square ex prime hat, and now we just have to find out what is f frictional. So f frictional plus n minus ng along z direction minus, so minus we have 2m omega cross v. Your omega cross v is minus v omega, so that becomes plus 2m v omega, and it's in the which direction is it? And along ey prime direction. And similarly, you get minus m omega cross r, and minus m omega cross r would become plus m omega square r ex prime hat. So all this should be equal to 0, and we can see the only forces acting in the z direction are n and ng. So this gives n equal to ng, and along the x and y direction we get the frictional force or some kind of a contact force, let's say, is minus 2m v omega ui prime hat minus m omega square r ex prime. So in the x prime y prime direction, we see that there's one component which is along minus x prime direction, one in the minus y prime direction. So you have a f frictional is acting along this direction. We'll come back to the physical interpretation for why this frictional force should be acting in this direction. But let's just move on to part B, where we know that the velocity so now we have to find the frictional force again, but the velocity is in the plus x prime direction. So I would let you do this same. We'll just follow the same expression. So F in the rotating frame, just total force which is 0, nothing but F in the lap frame minus m d omega by dt cross r minus 2m omega cross v in the rotating frame minus m omega cross r. Now again this is 0, and we'll have to just find out these two expressions. Again, this remains the same from previously, whereas here the expression changes, v goes to minus v. So I'll let you verify that this is nothing but n minus mg from ez hat. So this comes ez prime hat, which comes from f lab, and then you have f frictional force. So instead of plus 2m omega v, now we'll get minus 2m omega v ui prime hat. This is because here instead of plus, we get a minus here because v has flipped sign, and the last term remains the same. So which is m omega square r ex prime. So again, along z prime direction, we just have n equal to ng, and we get f frictional force to be equal to 2m v omega ey prime hat minus m omega square r ex prime hat. So these are the two components of this frictional force. So again, we'll just try to. So we have one component which is in the plus y prime direction, and another component which is in the minus m omega square r x prime direction. So it's minus ex prime hat. So it's coming towards O, and there's one which is perpendicular. So we have a frictional force which is somewhere along this direction. Okay. So this brings us to the last part where velocity is now only z prime direction. So 0 would be equal to f minus m d omega by dt cross r minus 2m omega cross v in the rotating frame minus m omega cross r. So here there's an interesting observation. So this is again 0, the rotation rate is 0. The interesting observation is that omega cross v, the velocity is now in the z minus z prime direction. So when we find omega cross v, what one gets is that you get Ez prime cross Ez prime. So Ez prime cross Ez prime is exactly 0. So you don't have any Coriolis force when the ant moves in the vertical direction. So because when the direction parallel to the rotation axis, the omega cross v cross product becomes 0. So our f, so this gives n minus ng and Ez prime hat 0 to plus f frictional force, which is nothing but m omega square r e x prime hat. So this gives f frictional equal to minus m omega square r e x prime hat. So we'll again try to see how that's x prime, y prime, z prime, and we see that there's just one force which is along minus ex prime hat. Okay, so these are the frictional forces in all these three cases, or some kind of a contact force, let's say, in these three cases. And now we'll try to look at why do we get these directions, and what does it physically mean. So let's go from backwards. So let's say we start with C now, instead of going again from A. So in the case C, so we'll have some qualitative. So quantitatively found out, we have some qualitative analysis, a qualitative picture, a physical meaning behind why we have frictional forces in this direction. So to get a qualitative picture, we'll go back to the inertial frame. So we have found out we have used the rotating frame to get the expressions, but we'll go back to the inertial frame to understand. So we'll go to part C. So we found that there's a frictional force which is acting along Ex prime hat, but in the minus direction. So it's coming towards the center. So for the C case, this F prime direction, F prime, the frictional force, if we look at it in the inertial frame, this is the force which is responsible for the centripetal acceleration as the ant goes around. Since the ant is rotating, since the ant is rotating with the rotation rate omega, the velocity vector, tangential velocity vector, changes direction, and you need a centripetal acceleration for the velocity to change direction. And this frictional force is the one which is giving the centripetal acceleration in the inertial. So this is slightly simpler to understand. Now let's go to the B case, where we found. So in the B case, we found the frictional force to be along plus y and minus. So it's along plus y and minus x prime direction. So you have one component which is along x prime but in the minus direction, and one another component in the y prime direction. So in the inertial frame, this is nothing but one along the radial direction and one along the tangential direction. So the radial direction, again, we can use the same argument as before. This is the one which is providing centripetal acceleration for the velocity of change. But the tangential acceleration provides another purpose. This is nothing but, since the ant is moving away from the center, so it has a velocity, I remind it's along Ex prime hat direction. So it's moving away from the center. So its tangential velocity is r omega, and r is increasing. So the tangential velocity is increasing. So the ant requires some kind of a force which can provide this increase in the rotational velocity or the tangential velocity, and this one component of the frictional force is responsible for providing this tangential velocity to increase with time. So these are two components of the frictional force, and one gives the centripetal acceleration, and the one gives the tangential acceleration for it's required for the ant as it moves away from the center while continuing to rotate about the axis, which is O. Now let's come to the last part is now let's A. Since we are going from C to A. So this is our x prime, y prime, and here x and y. So in this case, in A we found that the frictional force is in the minus x prime direction and minus y prime direction. So we have some kind of frictional force along this direction, and it has one component along minus x prime, one component along minus y prime. So in the inertial frame, you have one velocity field which is along, or one force which is along minus x prime direction. So again, this provides the centripetal acceleration necessary for the ant to rotate about the center O. The other one gives a negative tangential acceleration, and this again is because the ant is moving towards the center, its radius decreases, and which means that the tangential velocity should decrease with time. So this deceleration, this tangential deceleration, opposes the velocity and it reduces the rotational velocity or the tangential velocity as the ant moves closer and closer towards the center. So now we have come to the end of tutorial 1. So we have looked at a problem where we have rotating frames and a linearly accelerating frame, and we have tried to understand the force balance, the velocities in these two frames of references, in the frame of reference of a linearly accelerating frame, the frame of reference in this corresponding inertial frame, and also a frame of reference which is rotating, and in an inertial frame which is not rotating. So this brings us to the end of tutorial 1, as I said, and we'll meet again in tutorial 2. Thank you.